won't be able to log in just yet. Go ahead and get ready to log in here, but I got to get it started here. And then we're gonna get your notes out. Also, we'll be going through the same thing we went through last week a couple different times with the review. So you probably have all this stuff in your notes already, but just to hit it again, those of you that were gone, obviously, hopefully you've had a chance to see the videos, the worksheets up there. Now, if you're ever gone and you go to the assignment page and see what the assignment was, and I'll typically always attach the worksheet. Even if you can't print it, you can always do it. You can look at it online and put it on other paper. That's not a problem either. So I try to make everything available to you that we had, that we were working on. So all right, what am I looking for? Okay, begin class. Okay, now you should be able to log on. Oh, no, you won't either because I don't have it plugged in. Okay. Now, and it may take just a little bit here if you want to wait. It may take a little bit to get the signals connected and everything. But all right, so while that's happening, we'll talk about everything. We really don't have anything new. I do want to add in the definition, I guess, of differentiable. I think maybe that came up on one thing. We've talked about it. I mean, it was on our last quiz in the directions, and we just, in a very informal way, talk about differentiable. So it's not really anything that's a big deal when it comes to the quiz or anything. So otherwise, there really is nothing new to be talked about. We'll go over the homework. And then talk about any things that are missing. Maybe there's a few review problems that I'll kind of give you, but it's definitely not an inclusive review. You'll probably it'll be more about going back over your homework and, the things we've done. And, so we'll certainly be making this is kind of a list of those things you need to be able to make sure you can do. And then you can just go back in homework, you can practice those things, and so forth. So we started the chapter here with the definition of the derivative. We later then changed those a's to x's, but it's the same thing. It's the slope between 2 points. This part of it, right, is this part is the slope between 2 points, right? What are the 2 points? A plus h and a. Those are the 2 points. H is the distance between the 2 points, right? And then this part, but the 2 points become 1, right? The 2 points become 1. H goes towards 0. H is the distance between the 2 points, so the 2 points become 1. So this is the definition of the derivative because it's a slope at one point A, right? Or if we put an x there, it's a slope at all the points x, so it can actually give us an equation of the derivative. But that's why that is the definition of derivative, because it's just slope. It's just slope, right? Subtract the y's, subtract the x's between 2 points, and then the 2 points become 1. So we worked out some problems kind of a long way. We also did one in class last week where we then did the calculators, which we'll look at on the back of your homework page, or that worksheet. We'll look at those here in a minute. Then we learned our rules for the shortcut, or the power rule, where we can bring that number down in front, decrease the power by 1. So you'll have a few, not a lot, but just a couple of those. Deal with some fractions a little bit, be able to do some of those. Okay? Limits, the big thing, the big new thing here, obviously in this chapter we spent a lot of time with, was this idea of limits. Okay? And limits, you had the worksheet with some of those. You had the earlier worksheet back on Wednesday with the algebra one, right? And so you've got a variety of ways we can do a limit problem. So here's a simple limit problem right here. First thing you do is substitute in. So x is approaching 2, you plug a 2 in, and you get a number, and that's your answer. So if that works, that's where you would start. Most of the time when you plug a number in, this is going to happen. Right? You're going to get 0 divided by 0. You get 0 divided by 0 basically means keep going. So if it's a no calculator problem, you would do these algebra things. Maybe factor and cancel. Maybe you get a common denominator or bow tie and cancel. Maybe you get multiply by a conjugate and cancel. So all those things we did on that worksheet, you may want to practice, go back to that worksheet and practice some of those again. And so some sort of algebra. So some things will cancel, and when they cancel, then you can plug your number in and get your final answer. And then the third situation could happen when you plug something in is you get a non-zero number divided by 0. 6, 7, 8 divided by 0. Then you just say does not exist. Does not exist. Okay? Now, if you're looking at a graph, then you can think of that video we did. Do the cars meet? Right? If the cars don't meet, then the limit doesn't exist. Okay? If the cars don't meet, the limit doesn't exist. So this graph's coming in here, this graph's coming in here, they don't meet, limit doesn't exist. But if they do meet, even if there's a hole there, if they do meet at a point, then that y value is your limit. Okay? And then, of course, our tables is just another way of seeing if they meet, right? We look at the table, and that's, again, what you were supposed to do on the back of that worksheet. So we can look at that. You look at a table, and as x approaches 2 or x approaches 0 or whatever, you see if those y values are meeting at some value, and then that's your limit. Okay? That's it. That's the various ways we can solve a limit. So you'll have a fair amount of that on the quiz because that's what we've probably spent the majority of our time talking about. And then section 2.4 was the chart stuff. Now that we have this nice little power rule with where we can bring the power down in front, we can find some equations of functions, some derivative equations. We can do our local max and min. And of course, the key to local max and min and increasing, decreasing is where do you look for local max? What's happening at a local max? What's changing? Okay, you're missing it. You're missing it. What is the key thing that's happening at a local max? The slope. Okay, you guys are good. You're good because you're really focused in on what you need to prove and show. So that's a good thing. But you're making it harder than it is. What happens at a local max, a local min, or a flat spot? There we go. Slope is 0. That's what you want to focus on. I made it harder by saying local max. I should have said local max, local min, flat spot. The slope is 0. That's the key. The first entry in the chart is what? Where the first entry is local max, local min, flat spot, which is when the derivative is 0. Most important thing, right? It's the first entry in the chart. Okay? We care about when f prime is 0. So if we have an equation for f prime, we can set it equal to 0 and solve that thing. Then you get into what you guys were talking about, right? The positive, the negative, and all that stuff. Yes?
How much of that is going to be on our test?
A little bit, yeah. Like 54. We'll look at 54 today. There was another one. Okay? Those were those kind of chart kind of problems.
So like how much points of our test? If I was going to fail that part of it.
Oh, don't think like that. That's not here. Yeah, we did that thing with antiderivative. No. Now, okay, let me back up a minute. There could be something with the big F, just the notation. But that rule, you know, where we talked about doing it in reverse, we talked about doing the derivative rule in reverse, right? Instead of, dividing by the new power stuff, none of that. None of that. Okay, but as far as understanding that big F, big F, and then little f prime, that this is the order that those would go. And big F, the derivative of that is the same as little f, knowing that. And big F double prime is the same as that one. Yeah, I mean, that connection, there may be something about that. Yeah. Maybe. It would be a small piece of what you would do. Okay? The other thing that is not on here is the thing we wrote down on Friday. So let me put that on here. About a function, I'll just rewrite this. You already wrote this in your note. But a function f is continuous, right, at x equals a, if, right, and the first thing was what? F of a is defined, right, must be defined or is defined, to limit as x approaches a of f of x exists. We said must. Yes, last time, remember, my grammar was bad last time. I should have written, for a function f of x to be continuous at x equals a, f of a must be defined, the limit must exist, right? That was the language I was using last time. if I say it this way, a function is continuous if f of a is defined, if the limit exists, and if the limit as x approaches a of f of x equals f of a, right? And we have those three things, and you needed to memorize that from the standpoint of you need to be able to look at those as stating why a function is not continuous. Now remember, continuous basically means it's broken somewhere. There's something, some hole or break or gap in the graph, something that's not continuous, right? Continuous is just unbroken. Never lift your pencil. So what are those? Well, you could have this situation where the function is not defined. That's a problem in a graph. That's not continuous. You could have a vertical asymptote situation, right? You got a situation where the function is not defined, right? Those are problems in the graph as far as being nice and unbroken, nice and continuous. The limit must exist. So you can't have this situation, right? Like in a piecewise. Or, again, vertical asymptote. Vertical asymptote breaks both of those conditions, right? The limit doesn't exist either. The cars don't meet, the cars don't meet, right? So the function is not continuous at those places. And then you got this situation here, which is the diner burned down and then you got a new spot there. Because that actually meets these first two, doesn't it? Is the function defined in that scenario? Yeah, there's an output, right? There's an output. Does the limit exist here? Do the cars meet?
Yeah.
Sure, cars meet. Problem is, those are two different places, right? The function output is different than where the cars meet. So you not only have to have an output, you not only have to have the cars meet, the limit has to exist, but those have to be at the same place. And if you've got those three things happening, then that graph is going to be nice and smooth and unbroken. So we had that written down last time. We've got those that we need to know. So if I give you a picture of a graph, and we'll talk about one of those again later today. Okay? And then I guess the last thing I would say would be, if you want to write this down, differentiable. A function, let's just put that in here, and then we'll go ahead and work on the homework. And as we go, we'll talk about how it connects to all these different things here. A function f of x is differentiable if f prime of x is defined everywhere. Now, when is f prime undefined? When is f prime undefined? Sharp point, vertical asymptote, right? When you got a not vertical asymptote. Well, you're right, but you're right, vertical asymptote, because there's no point there, right? But I was thinking vertical tangent line, vertical tangent, right? Because when's the slope undefined, right? Vertical tangent. So examples of things that would make it not be differentiable would be your sharp point and a graph that came up and did this, right, where you had a vertical tangent. Those would be situations where the derivative would be undefined, so therefore it is not differentiable. Not differentiable. Okay? Now, would those two functions that I just drew there be continuous? Continuous.
Yes.
They're continuous. They're not broken, right? The cars meet, right? The cars meet there. The cars would meet right there, right? There's no holes or there's nothing weird. So a function could be, again, it's like the square and the rectangle, right? So let me write that down. A differentiable a differentiable is always continuous, right? So if you know a function is differentiable, it's automatically continuous. Because if the derivative is defined everywhere, I mean, that you can't have any weird stuff going on, right? It's just got to be nice and smooth. And that was the word we used on the last quiz, was smooth, when we were talking about differentiable. Okay? A continuous is not always differentiable. Because I have two examples right over there that are continuous, but they're not differentiable. So a continuous might not be differentiable, but a differentiable is always continuous, right? A square is always a rectangle, but a rectangle might not be a square, right? So the square is the more specific situation, and differentiable is the more specific situation. Differentiable. If you know a function is differentiable, you automatically know it's continuous. I don't have to tell you a function is differentiable and continuous, right? Except in one little technicality, which we won't talk about until chapter 4. So okay, so it's a differentiable is always continuous. Okay, so that's automatic. So if the derivative is defined everywhere, so the word differentiable, remember, the act of taking a derivative is called differentiation. Differentiation is the act of taking a derivative, right? So if it's differentiable, it means you can take the derivative. You can do differentiation. So the derivative is defined everywhere. Okay? All right, and here's two examples that are not differentiable, because those are the two situations where the derivative would not exist or would not be defined. And also any broken kind of situation, right? Same thing. But that's fairly obvious. Okay, there you go. That's it. So let's take a look at some homework. Let's look at the 2.3 stuff first. So we had, what do we have, 61? And 63 through 67. So 61, suppose that f of 2 is not defined. Is it possible that the limit as x approaches 2 exists? Is that possible? Yeah. Yes. Justify your answer. Right there.
Boom.
Right? Now it'd be good to put a 2 and maybe an xy axis and put a 2 there or something, right? But there you go. F of 2 is not defined, but the limit exists. The cars would meet.
So, like on the test, we could use pictures as our.
I love pictures. Now, words along with pictures are usually helpful, right? You know, some words along with pictures. And I would avoid words like cars don't meet and stuff like that, you know. I would avoid those kind of words. What you would want to say instead is, if this was my picture and here's 2, and then this was, say, 4, you would say, for example, f of 2 is undefined. If you really wanted to be specific in answering this one, you know, which I think if it was a quiz and my grade was kind of riding on it, I might say, hey, maybe I should be specific and not trying to cut corners here, right? And, you know, so that's up to you, but that's kind of how I would think. So here's an example where f of 2 is undefined and the limit doesn't exist. Now, if you really want to give a good reason why the limit doesn't exist here, you would say, instead of cars don't meet, you'd say the limit as x approaches 2 from the left is equal to 4, and the limit as x approaches 2 from the right equals 4. That's what you really mean when you say the cars meet, right? From the left, you're hitting a y value of 4, and from the right, you're hitting a y value of 4. Right? That's the language, that's the mathematical language when you talk about the cars meeting. If the cars don't meet, it would be because from the left you hit 2 and from the right you hit 7, right? That's why the cars don't meet. The limit from the left is different from the limit on the right, okay? So, yeah, we'd want to try to talk in mathematical language a little bit. But, if you drew a little picture of a car and said the cars don't meet and stuff, and it's pretty obvious you know what you're talking about. You probably would not lose too many points, if any. Okay? So I'm not real picky there, but this thing we had up here earlier with the 1, 2, and 3 and the continuous, right? Those things, right? I don't want you to say like so. If I asked, and we'll touch on this on a problem later on, but if I ask why is it discontinuous then? You got those 3 reasons. I don't want you to say because there's a hole. or because you have to lift your pencil, or because there's a break, right? I want you to say one of those examples that I was given there. So that I'm specifically telling you about. But you want to use good mathematical language. All right. Suppose that f is continuous at 3, and the limit as x approaches 3 is 17. So again, that would be kind of like here's 3, and up here is 17, right? And it says the limit as x approaches 3 is 17. So the cars are meeting at 17, okay? And it's continuous. So let's see what it says. Might be true, must be true, can't be true. So 3 is in the domain of f. Now what's that mean, it's in the domain? It means more than it's an input. You're right, domain is the inputs. But to be in the domain, it means if it's an input, it has a output, right? That's what it's saying. That's another way of saying that f of 3 is defined, right? We were talking about that when we said f of a must be defined, right? That's what it means to be defined at a point, is that you plug something in and you get something out. That's what it means to be defined, okay? So when it says 3 is in the domain, it's saying when you put 3 in, you get something out. Because if you don't get anything out, it's not in the domain, right? You can't put -3 into the square root function because you don't get anything out. You don't get an output, okay, of square root of -3. For the real numbers anyway, right? We're not talking about the imaginaries. 64, does f of 3 have to equal 17?
Yes.
Since it's continuous, the limit, they already told us the limit, the cars are meeting at 17. If it's continuous, the limit and the output have to be the same. So f of 3 has to equal 17. The limit as x approaches 3 from the left equals 17. True. If the cars are meeting there at 17, the limit on the left has to equal the limit on the right. So, good questions that just make you think about these things we were talking about. So all of those must be true, I guess, right? Must be true. All right, 66 is one we talked about at the end of the period on Friday. Again, this gets at this idea of continuous functions. When is a function not going to be continuous? Well, if you look at those pictures we were just drawing a minute ago, it's usually in things that look like they might be. A lot of times it's in piecewise kind of things, right? So you can expect a piecewise to be in the picture on something like this. So on 66, they give you this piecewise. Now, if there's going to be a problem on that piecewise function, where's it going to happen? Where it switches from one to the other, right? Which in this one happens where? At 2. So we're really only interested in this problem where x is 2. At the other places, it's going to be fine. Over here, over here, over here, over here. Function is going to be continuous because what you have is a line and a parabola, right? And those are fine. Those are nice continuous graphs, right? But at 2, we might have a problem. So it says find the value where the limit as x approaches 2 exists. Well, would the limit exist here? The cars meet? Is the limit on the left equal the limit on the right? No. So to be continuous, what has to happen? For the limit to exist, what has to happen? Their y values, their outputs have to be the same at 2, right? So how do you tell what their y values are at 2? You plug in a 2. You plug in a 2 for x. So we plug in a 2 into the first one for x, and we get 2a plus 1. And we plug in a 2 for the second one for x, and we get 4. Those two have to be equal, right? So I put a 2 into x on the first one, and I put a 2 into x on the second one, and those outputs have to be the same, and then I wouldn't have this situation. The one would end, the other one would take off from the same spot. Okay? So we get 2a equals 3, a equals 3/2. So we found our value of a. If a has the value found in part A, does the derivative exist there? So interesting. We have a line that comes in at 2. It ends with an open circle, and then we have a parabola that takes off. Now, what if that parabola takes off like that? Does the derivative exist there? Oh, and this would be filled in, by the way. Wouldn't that create a sharp point? I mean, can't you see that happening? You got one graph coming in and another graph taking off. Well, what might happen is there's a sharp point there. Even though the one ends and the other takes off, it may not take off at the same slope as the other one, right? So this kind of gets at the word at differentiable. Well, that's exactly what has to happen. For f prime to exist right there, and this probably is beyond what I'm going to worry about for the test. I want you to be able to do this first part. I want you to understand this first part with the limit, and they meet, and they have the same output. But what you have to do here is, would they have the same slopes? Well, we have a rule for slopes. If you've got the graph ax plus 1, that's a line. What's its slope going to be? A, right? It's a line. So that line comes in, it's going to have the slope A. Now, we already found that. That was 3/2. So the line's going to come in with a slope of 3/2. And the parabola is x squared, right? That's that equation. What's its slope? What's its derivative? 2x, right? So the parabola has a derivative at 2x. Now, what's our x value here we care about? 2. So put a 2 in. 2 times 2 is 4. So the parabola at 2 is going to have a slope of 4. So the line has a slope of 3/2, and when the parabola takes off, it's immediately way steeper at 4. So does the derivative exist? The question would be no. There'd be a sharp change in direction. That would create a sharp point. So what we've looked at in chapter 1 is mostly just about sharp points when we look at a graph. We can see sharp point. Oh, okay. What they're saying here is this is what that would look like in an equation form. We got a piecewise function. If you want to know the slope of each piece, do the derivative of each piece, right? And we have that little rule for derivatives. Okay, so that would be if you have questions on the quiz that are easy, medium, and hard, that last piece of that one would be one of the hard ones, right? There wouldn't be probably a ton of that on there, but every once in a while, you definitely have something. Okay, so that was what was going on with part B there in 66. And then did we do 67 or not?
Yeah.
67. So we have another piecewise function. It says it's continuous at 2. And it's defined by this rule. So find the value of A. So what I would tell you on 67 is it's exactly like 66, but they ask the questions differently, right? In 66, they say find the value where the limit exists. Well, what that means is they have to meet, right? Well, that makes them continuous, right? That they meet and that there's no gap there. So when they say find the value of A, they told you the directions is continuous. Well, what that means to be continuous, when you plug in a 2, you've got to get the same value. So let's plug a 2 in for x on the first one. 2 squared is 4, so we get 4a plus 3. Okay, let's plug a 2 into the bottom one. We get 6 minus 5, which is 1. So they have to have the same output. So I put a 2 in for x into each of them, and I get that. So I get 4a equals -2. I get a equals -1/2. Right? So I did exactly the same thing I did in 66. But the question was asked a little differently, but it's really the same question, right? To be continuous, they have to meet there, okay, just like for the limit existing. Is f differentiable at 2? Well, what we learned differentiable is? The slope is defined. In 66b, they say, does f prime exist, right? Is f prime defined? Same question. So does a derivative exist? So we'll do the derivative of each of them. So what would be the derivative of ax squared plus 3. Well, what's the rule for derivative here? Bring the 2 down in front. A is just a number, so we'll just leave it there. Well, we know what it is, actually, but we'll get to that in a minute. And then x to the first plus derivative of 3, 0. So we got that. Now remember, we know a is -1/2. So 2 times -1/2 is -1x, right? And what's x in this problem? What do we care about x? Is it differentiable at x equals 2? Right? So we put a 2 in there. We get -2. So for the parabola, the first part of the piecewise, we got a slope of -2. We're going to see if we got a slope of -2 when it's going out, right? So the function coming in has a slope of -2. Going out, what slope does it have? Well, the function going out is what? 3x minus 5. What's the derivative of that? Well, it's just 3. That's just a line, right? The derivative of a line, the slope of a line is 3. So, got to have a sharp point. The function coming in is -2. The one going out has a slope of 3. There's a sharp point. The derivative doesn't exist. Is it differentiable? No. Okay? So, to be continuous, they have to have the same y value, so they meet. to be differentiable, they not only have to meet, but they have to be nice and smooth. There can't be a sharp point there. And so we check their slopes, which means they're derivative. All right. Good stuff, good stuff. Now, let's move on. So that's kind of the end of section 3. We'll come back and we'll look at some graphs. We'll look at some more limit problems because that's what section 3 was about. Let's move on to section 4. This is where we got into the stuff with the chart, okay, and those kind of things. And we've done a few of those. We did number 21 together. No, was it? We did number 19 together on Thursday. You were assigned number 21. We worked number 21 in class. And then I gave you number 20 as an assignment today. So let's take a look at that. So number 20 says S of t equals negative 8 t to the 9th plus 9 t to the 8th minus 7th. And they want to know where S is increasing, where S is decreasing, where S has a local max, and where S has a local min. That's what they're asking for. Okay, so what do? We said this earlier today. Do the derivative. So we want to find S prime and see where that is equal to 0, right? Because local max, local mins, those kind of chart stuff. And we got our chart right here. What do we care about on the chart? Right here on the S prime line. This is S prime. Care about where S prime is 0. That's what gives us all this stuff right here. So we go to S prime, and that would be what? Negative 72 t to the 8th plus 72 t to the 7th. Derivative of that, 0. And we're going to set that equal to 0. So write that out like so. Nice thing is, there's a lot of nice things there that we can factor out. A 72 t to the 7th, we would end up with negative, I probably should have taken out negative, but whatever, negative t plus 1. So we set each of those equal to 0, so either t equals 0 on that one, or t equals 1, right? T equals 1. Solve that one. So what did I just find right there? What are those called? You have roots, but just found the stationary points, right? I found where the derivative is 0. Those are the stationary points. Those are the places on the graph. If we were doing a graph, those are the places where the slope would be 0. Either a local max, a local min, or a flat spot. Okay? And how do I tell? Well, I need to tell if the graph was going up or down. Well, what's S prime tell you about the graph going up or down? That was the part you guys were trying to tell me earlier. When S prime is positive, what's the S graph doing? Increasing, going up. So that's what I need to know now. I need to know when is this graph going up or down. Sure be nice if I had an S prime graph over here. That's what we did in chapter 1. But we don't. I have no idea what that graph looks like right there. Okay? So I'm going to make myself a number line. Put a 0 on it. Put a 1. And when I say an S prime number line, what I'm saying is I want to find out what the Y values of S prime are for some of these X values. I want to know, or T values in this case. I want to plug those in, and I want to see if I'm getting positives for S prime or negatives for S prime. So negative 1 I could put in. Let's see, I could put in a half. Between 0 and 1 I could put in 2. Right? So let's put those into S prime. Let's start with negative 1. So I would say put it into this version would be the smart thing. So negative 1, what's negative 1 to the 7th? Negative 1 times 72, that's going to be a negative. I don't care that it's negative 72, I just care that it's negative. Put a negative 1 in here. Negative 1 is 1 plus 1 is 2, so I'd have a negative times a positive, that's a negative. All right? Put in a 1/2. What's 1/2 to the 7th? Positive. I have no idea, but it's positive, right? And put a 1/2 here. I have negative 1/2 plus 1. Isn't that positive? Negative 1/2 plus 1, that'd be positive 1/2. So positive times a positive is positive. Let's put a 2 in. 2 to the 7th is positive. Negative 2 plus 1 is negative. So positive times negative is negative. So what's this tell me that the S graph is doing? Down, up, down. Local min, then a local max. I got a local min right here. So a local min at x equals, not x, t equals 0. I got a local max right here because S prime changes there. So this is t equals 1. Where is S increasing? That would be between 0 and 1 because S prime is positive. And where is S decreasing? That would be from negative infinity to 0 and from 1 to infinity because that's where S prime is negative. And remember, let me write it out. I'm going to do this one time. For local max, I would say t equals 1 because S prime changes. What was that, local max? Positive to negative. So S changes increasing to decreasing. You have to have that. If I ask you to justify why something's a local max, I want to see that written out just like that, both the S prime and the S part. S prime is changing from positive to negative, so S is changing from increasing to decreasing. That makes a local max. Okay? Yeah, that, point-wise, that's a fair amount. I mean, that's like 5 points right there. On the quiz, you probably get a point for doing the derivative and setting it equal to 0. You probably get a point for finding the stationary points. Probably get a point for putting them on a number line and plugging values in and getting something that looks like this. You probably get a few points here for each one of those answers. I mean, geez, that's already like 6 or 7 points, right? Probably another point in there for your justifications. All right? So, yeah, we've done 3 of them now. And we're about to do another one when we do 54. Matter of fact, let's do that one right now. Okay, so let's go to 54. Okay, page 122. A particle moves on the x-axis in such a way that its position is given by the function x of t equals 3t to the 5th minus 25t cubed plus 60t. So what does that mean? So if I plug a 1 in, let's just say I plugged a 1 in and got out a 10. I don't know what you get, but let's say you got a 10. What would that 10 tell me? Its position on, what's the problem saying? The x-axis. So imagine we had an x-axis just sitting down here in line. This problem's like an east-west Bismarck thing. That's what it is. It's an east and west of Bismarck thing. It's the position. Here's my x-axis. Here's 0 right in front of Casey. Right? And I plug in a 1 and I get out a 10. So what's that tell me? At 1 whatever time unit, I'm over here at 10. Now what if I got negative 10? I'd have been over there. Now does that tell you anything about which way you're moving? If I plugged in at 1, that'd be like saying x of 1. Now, one weird thing about this is x is actually our output, isn't it? That's weird. X is the output. But why? Because it's our position on the x-axis, right? T is the time. X is the output. So if I ask for x of 1 and got a 10, that tells me I'm here. Does it tell you about which way I'm moving? Doesn't tell you anything about which way I'm moving. I might be stopped. Just tells you I'm 10 miles east of Bismarck. Right? I'm at positive 10. That's my position. What do you need to know to tell which way you're moving? I guess I jumped ahead. What's the question asked? When is a particle moving to the left, right? So that's what I'm thinking. I'm thinking to myself, well, do I know if I'm moving to the left here? No, I have no idea. What do I need to know if I'm moving to the left or westward? Well, okay, what's the car language? Speed, velocity. Speed or velocity, right? Velocity, actually, because speed's always positive. So I need to know the velocity, right? Positive velocity, which way am I going? Come on, we did this with Bismarck, right? Positive velocity, which way am I going? east, to the right. But in this problem, it'd be left and right. This problem's not about east and west. This problem's about, but I want to compare it to something we've done before, right? So when I'm moving to the right, my velocity is positive. When I'm moving to the left, my velocity is negative. But how does velocity relate to position? Somebody said it. Somebody said slope, but what's the word? It starts with a D. Derivative. Derivative, right? Derivative. We did that at the very beginning when we first talked about derivatives. We talked about the position from Bismarck, right? And then we talked about the velocity was the derivative, right? We called it P. We called the function P, and then we said P prime was the velocity. So it's the same thing, okay? So what do I need? I need to find the derivative. So I need x prime of t. And I've got to figure out when the derivative is, what's it say when it's moving to the left? Left. So I care about when the velocity, the derivative is negative. I want to know when the derivative is negative. Too bad we haven't recently done a problem where we found out if the derivative was positive or negative, because that'd be really helpful right now, wouldn't it?
All hope's lost.
Oh, all hope is, oh, wait. Oh, wait a minute. Number 20. Number 20, what did we do? We did the derivative, we set it equal to 0, we made a number line, we plugged numbers in, and we found out if the derivative was negative or positive. Oh, awesome. Okay, but now, seriously, see the connection, right? When we first talked about derivative, we said we can think of it two ways. We can think of it as slope, we can think of it as rate of change. Rate of change, we used the car example with Bismarck, right? So when we've been doing these, like number 20, we were thinking slope. We were just thinking math stuff. We were thinking of a function. Local max and min meant when it went up and down. Now let's put that in the car language. So what's a local max and a local min? On this problem, we were talking about the graph went up and then down and back up. What would that be if I was driving east to west of Bismarck? I would be going east when it's going up, right? Be going east, and then I would stop, and I would turn around and go back west, right? And then I get to the minimum, and what happens there? Stop, go back this way, and what if I had a flat spot?
Stop, take a deep break.
Stop, take a break, and then keep going the same direction, right? So if this was a car language, a motion, a position velocity problem, this would be going to the left, stop, go to the right, stop, go to the left. So the local maxes and mins and flat spots relate to the points when you stop, right? And the slope, the derivative positive negative, is the direction. So this is exactly, 54 is exactly the same problem as number 20. One is in slope language, one is in car language, which is how we first learned about derivatives, okay? Now, first time we're doing these number line problems, I would expect you'll get it in the function type language like 19, 20, and 21. Local max, local min. But be ready, the very next quiz after this and all year long, we're going to see these kind of problems. This is the first one you've seen, but about a particle moving on the x-axis. Those are really popular problems on the AP test because they get at that east-west kind of thing, which is the very first thing we did with derivatives, was the car moving east to west of Bismarck. Okay, so let's do it quickly here. The derivative would be 15 t to the fourth minus t squared plus 60, and we want to know when that equals 0. Don't forget the equals 0. That's the key. We want to know when the car stops, because we can't tell when it's going left if we, from when to when. Well, when does it stop going left? It has to stop, right? So it can go back to the right. So we have to find when the car stops if we're then going to find when it's moving to the left. That's the key. So we start by doing the derivative equals 0. Now 15 goes into all those. Oh, gee, t doesn't though. Shoot. So let's take out a 15. We get t to the fourth minus, what is that, 5? Right? T squared plus, oh, that makes it easier. Now we can FOIL that, right? And this would be t squared and t squared. Minus 1 minus 4. Minus 4 minus 1 be minus 5. There we go. Okay? So this would be, when does 15 equal 0? Oh, never, so we can ignore that. What about this? T equals plus or minus 1, plus or minus 2, right? Yeah, you could factor those. T squared minus 1 would be t plus 1, t minus 1. T squared minus 4 would be t plus 2, t minus 2, right? You could do that too if you want. Okay? Now, t is time, though, in this problem. What did they tell us? They said t is positive, right? T is time. So we can ignore the negative ones. If this was just a math problem, we wouldn't, right? But it's a velocity kind of a story problem. So we could throw out the negatives. So all I really need to know is that 1 second or 1 minute or 1 hour, I don't know what the time unit is here, it doesn't matter. But at 1 and 2, this particle is stopped, right? At 1 and 2, it is stopped. Now, did it go left and go back to the right, or did it go left, take a break, and keep going left, whatever? Okay, who knows? But let's put some numbers in. So let's put a 0, let's put a 1.5, let's put a 3. This would be no calculator. You think, oh, great, I got to put a 1.5. Well, no big deal. I would plug it back into this version right here. Would be the easiest one. So let's put a 0 in. 0 minus 1, negative. 0 minus 4, negative. And, of course, 15 is always positive, so I don't really even worry about that. Negative times negative is positive. So the car is going to the right before 1, so we don't want that. 1.5. Now, what's 1.5 squared? I don't even know. I do, but I wouldn't have to figure it out. But I do know it's bigger than 1, right?
Yeah.
So 1.5 squared minus 1, that's going to be positive. 1.5 squared I know is less than 4, so this got to be negative. So positive times negative is negative. And then put a 3 in. 3 squared is 9 minus 1, that's positive. 9 minus 4, that's positive. All positive. So this is going left between 1 and 2. But it's exactly the same problem as number 21. So it's good practice at doing that again. But it's just in a different context.
You could say it was a flat spot. If it was a flat spot instead.
If it went negative, negative, positive, right? So when's it moving to the left? So what would you put for your answer? Yeah, now actually, since they said t is greater than 0, we probably wouldn't need to say negative infinity, right? I mean, so that's a little misleading. But if it went negative and then a break and then negative, I think when it says going to the left, you could still say that whole time, all the way till 1. I don't think you'd have to leave out that spot when it stopped. I wouldn't make a big deal about that. Let's put it that way. If you left it out and said, well, it's not going left, it stopped. That's a tricky one because you're right. We said with the decreasing, even when it flat spots, it's still decreasing, right? So when you talk about that, that's kind of interesting. So if you explained yourself, either way, I would be okay with that. So I wouldn't worry about it. Okay? All right. That's 54. So let's talk, while we're on this same subject, let's look at 52 because it's kind of the same idea. This was much more challenging. I would not expect you to do one like this on the quiz, so we won't worry about it from that standpoint because there's this k in there, right? They give us this cubic, but there's a plus k at the end, right? Okay, well, tell me what the function is.
X cubed minus 3x squared.
Minus 3x squared plus k. All right, now, I know something about cubics. I know that they can go up and then come down, especially with a positive leading coefficient, right? It's going to start up, then down, then it could go back up again, and that's the most it could do. Now, it might just be it might not have any humps. It might have just a flat spot, or it might have, I'm going to go with this for now. Now, what's the plus k do? That's just going to basically shift this thing up and down, right?
Yeah.
Like so. All right, so what they want you to do is they want you to find what k is. So it says, for which value of k does this graph have just one intercept, x-intercept, two x-intercepts, or three x-intercepts? So the way I've drawn it right now, how many x-intercepts? One. Now, what would have to happen for it to have two? It'd have to shift down how far? So that bounces, right? So that point just touches the curve. It would have two. Then when would it have three? Shift down a little farther. But if it kept shifting down, pretty soon it'd go back to two, right? Whenever that point is just touching. And then if it kept going down, you'd be back to 1. Do you see what's going on? So what seems to be the critical element of whether there's 1, 2, or 3?
At the bottom, those 2 points, local maximum.
There you go. We have a name for it. The local max and local min. So if we can only find the local max and local min, if we only had a way of finding local max and local min, we'd be in business. Oh, we do, right? So 52 is really just like 20 and just like 54. Find the local max and min. Well, that starts by doing the derivative, which would be 3x squared minus 6x. What's the derivative of a constant? 0. So it doesn't matter what the k is, right? It doesn't matter what the k is. For the derivative, it disappeared. If that was a plus 7 or a plus 4 or plus 5, we do the derivative, it's just 0. So now we set that equal to 0. So we take out a 3x. We get x minus 2. So this would equal 0 when x is, that's one of them, or 0, right? So if x could be 0, or x could be 2. Well, that's got to be, and I already know, since I know this had a positive leading coefficient, I know it's going to have a local max first, and then a local min, right? I know that. Now, let's say you hadn't even thought of that, so you do a number line, that's fine. You can do that. Oops, that'd be a 2. We could put in some numbers here, right? Put a negative 1 into here. Negative 1 would make this negative. Negative 1 minus 2 is negative. Negative times negative is positive. Put a 1 in there. 3 times 1 is positive. 1 minus 2 is negative. Positive times negative is negative. Put a 3 in there. 3 times 3 is 9. That's positive. 3 minus 2 is 1. That's positive. Positive times positive. So I know it does that. So it goes up, goes down, goes up. But I kind of knew that. All right. So I got a local max. I got a local min. Now, but that's only part of the scenario, right? What do I need to know about that local min? When I shift that down, I need to know when it does what? Just touches. Which means it has an output of 0. When it touches the x-axis, it's got to have a y value of 0. Now, where do I get the y values of this function? From this equation, right? I need this equation. Now, before, we never plugged in or did anything with that equation, did we? But now, in this problem, I do. I need to know when that y value, when that minimum is going to touch that. Because then I'll have this situation. It'll come up, it'll touch, and now I'll have 2 roots, 2 x intercepts. Okay, so where is the minimum? The minimum is when x is 2, right? So I'm going to take that 2 and plug it in for x, right? So when x is 2, I get 2 cubed is 8. 2 squared is 4. 4 times negative 3 is negative 12 plus k, and I need to know when that is 0. So negative 4 plus k equals 0. K equals 4. These are the kind of problems that when we're reviewing for our midterm and stuff, these come up on the midterm, they come up on the AP test a lot. These are the ones that always throw us for the loop, because as soon as we see that K, we go, oh my God, I don't know. But as you're seeing here, we pretty much do a lot of the same stuff we always do, right? It does add a little bit extra to it. So when K is 4, we're there. Now remember, K is the shift, right? So K is a shift. So if K, so what's going to make this go down more? If K is, well, lower than 4, right? If K is lower than 4, it means we would not shift up as much, right? So at 4, we're getting just 2, right? So when K is 4, we're going to get just 2. But when K is littler than 4, we're going to have
Maybe 3, maybe 2, maybe 1.
well, right. So when K, but at least part of it is going to be when K is less than 4. Did I do that right? Is it? Yeah, I think so. When K is less than 4, we're going to have 3 for a while until the local max hits, right? Well, the local max is at 0, right? So let's plug that in for x. So 0, oh, that's easy. 0 minus 0 plus k. Oh, that's when k is 0. So when k is 0 is when this one will just hit. So isn't it between 0 and 4 when we're going to get 3, right? When k is between 0 and 4 is going to be that time where we're going to get 3 roots. And then when k goes, when it goes farther down, we're going to be back to just 2, right? So now we're going to be, at 0. So these are there's only 2 times we're going to have 2, right? The only times we're going to have 2 is when this one is touching, and then when this one comes down and touches, right? Which is here. So at 0 and at 4, we're going to have 2. When k is between 0 and 4, we're going to have 3. And then what? When k is greater than 4, it'll be up here, so we'll only have 1. And when k is less than 0, means we're farther down, and then we'll only have 1 also. That's tough. That extra stuff there was the tough part. But the key to being able to do that was understanding that the local max and min played the key role. That was really the key bonus. I mean, yeah. Sometimes I throw in a bonus. Have I thrown in a bonus yet? No. Seems about time. I haven't. Some of you probably know about this, have brothers, sisters, or heard. We do have a bonus the last day before Christmas.
Christmas.
The calculus carols. The calculus carols. So, yeah. So you'll have a bonus opportunity there to write and perform a original calculus carol or poem. If you're not a singer, it could be a poem. Instrumental's great. Yes, we've had orchestra people come in and instrumentals. We've had guitars. You can dress up. If you're not musical, a rap. Maybe we had a rap. I think one. We only had one. Solos are worth just a little more bonus points. Couple.
I'll do it by myself.
Couple. Not a huge deal. But you cannot get like 40 bonus points. No, you can't.
Can we do one by ourselves?
You can, but that probably is not more bonus points.
You can't judge on
But
talent.
for
That's
fun.
not fair.
All right. So yes, so that's coming. If you can't sing, you can do. So the idea is that you come up with your own lyrics that have to do with calculus, either the class or just the subject or both, whatever.
Like the class.
Like 'twas the night before the calc test, right? That's been a popular one. That's been the popular one, you know. Or it could be about the class, like, well, I've been compared to the Grinch multiple times, so if you want to do that, that's fine. You can do that too.
So you don't care?
Yeah, you can. This is your chance to take a shot at me.
So if it's an instrumental,
You still got to be school appropriate.
so if it's an instrumental, it doesn't have to.
Words? No, I want. Oh, okay. So you can use interest. Yes, it needs to have some lyrics. We need to have some lyrics. So you can play background for somebody else. All right. Here we go. We're taking. Oh man, time's flying. All right. So.
Oh yeah. That's like just too long.
Okay, let's go to that. Let's go to the limit page, 2.3. Go to 2.3, please. And I think I have a picture. Yes, here we go. I don't think we did this in homework. Go to page 111. 111. We did not do this one yet.
Yeah, so they give you a back. They can't rap. Wait. Yeah, you just said it.
Oh, you found the missing page there? It's just out of order?
Yeah.
They must have fallen out.
I
I
was
just
just looking
shoved
at
them back in
going
there
like
and they were
this.
reminded. All right. Okay. Shh. Okay, listen. All right, so we spent a lot of time on this part of it, okay? So doing that, we talked a lot about that continuous. We did those examples of continuous function, differentiable, little of that stuff. So back to the limit page. So let's focus on this a little bit. Now the graph ones, okay, let's talk about the graph piece of it. So here's an example on page 111. They've got this, and I'm looking at problems 27 through 36. Okay, and we had, on our homework, we had skipped that. We had done a couple different days with these limit graphs, but we had kind of skipped this section. So let's look at those real quick. So 27, so you expect to have, I would put this in the easier category, I hope, if we're looking at the types of problems. So you're given a graph, something like so, and it says, find the limit as x approaches -4 from the right. -4 from the right would be 0. The y value, right? The car's coming in at what y value? It would be 0. Okay? As x approaches -3. Right? There's a sharp point there. That doesn't matter when we're talking about limits, right? We're talking about limits. Sharp point only matters when you're talking about what? Does the derivative exist, right? Does the derivative exist? So is this graph continuous right there at -3?
Yes.
Is it continuous
Yes.
at -3? Absolutely. Right? You don't lift your pencil. There's nothing, right? There's no breaks, right? Continuous is just what the word says, continuous. It goes there, and then it goes there, right? Continues right along. It's not differential. The derivative doesn't exist there, but it is continuous. Okay, so the limit is 1. Next one is a limit as x approaches -2. Is that what that is? Did I read that right? As x approaches -2.
Yep.
What would that be?
1.3.
Are you guessing? I don't think you should have to guess, because isn't it over 2, up 1? So that's a slope of 1/2. So if you go over 1, don't you have to go up 1/2? So yes, so it would be 1.5 would be your answer, not 1.3. There'd be no leeway there. It is 1.5, because the slope we know of that line is 1/2. So over 1 would go up 1/2, so that would be 1.5. What about x approaches -1 from the right? That'd be this car's coming in at 1. So that would be the answer there. As x approaches -1, does not exist. The cars don't meet at -1. The right limit is different than the left limit, so it does not exist. As x approaches 0 from the left, that is also a -1/2. We know that because I can tell I'm going over 2 and down 3. Over 2 and down 3, that's -1.5. So if I go over 1, I'm going to go down, yeah, right, over 2 and down 3, that'd be -3/2, right? -1.5. So if I go over 1, I'm going to go down 1.5. Over 1, down 1.5. So I know that's a -1/2 right there. Okay? As x approaches 1, what's the limit? -2, right there where the cars meet. As x approaches 2, 0. As x approaches 3, 1. Even though there's a hole, doesn't matter. The cars meet right at 1, so the limit is 1. And then as x approaches 4 from the left, 2. Right? So, again, really good to envision that from that standpoint. So we'd want to be able to do those kind of limit problems. All right. So back to here. So that's what you look at with graphs. The algebra stuff we're not going to spend time on right now. If you want extra help on that, that worksheet we did last Wednesday, the factoring, the cancel, the common denominators, the conjugate, all that stuff, come see me. I'll be glad to work through that with you. There'll be a little bit of that, not a ton of it, but a little bit of that. Probably the emphasis mostly on the factoring part. That's the easiest of the 3, the one we're the best at. So be able to do those for sure. Let's talk about the calculators. So go ahead and get your calculators out here, and we'll Rachel, you're not logged in. What happened? Did it kick you out? Oh, you're in. Never mind. That was from a while ago. Okay, Rachel is presenter. So let's look at your worksheet. Let's look at the back side of that worksheet, and okay, so the thing here, the thing that happened on this worksheet was that most of them, not all, but most of them had no way of doing any algebra to them to be able to solve them. Now, there is two exceptions. There are two problems on here that we could have just done algebra to. So I guess we could practice a little algebra real quick. There are two of them we could have done algebra on. Can somebody tell me which ones? 5 and 3. 5 and 3 we could have done some algebra to. So as a bit of practice, let's do that. What algebra would we do to 3? Conjugate, which would be radical
1 plus h plus 1.
plus 1. And radical 1 plus h plus 1. So if you'd have been asked to do it without a calculator here, we could have done this. Now that wasn't what you were supposed to do on this worksheet, but just as a matter of review, let's do it. So I FOIL this. This times this is 1 plus h. Outers and inners would disappear. Negative 1 times 1 is negative 1. That's the top. The bottom is simply going to be this. Not going to do anything with the bottom. The 1's will cancel. The h's will cancel. Of course, I still have a 1 there. Now I let h go to 0. So this would be square root of 1, which is 1, plus 1 is 2. The answer would be 1/2. If I did some algebra to that. Okay? What you were actually supposed to do is you were supposed to recognize that, hey, this is not only a limit problem, it's one of our special ones. It looks like f of x plus h minus f of x. Actually, I should put a's in there probably for this problem. All over h. It looks like that, doesn't it?
Yeah.
So we were supposed to say, well, what function is this the slope of? Square root of x. Wherever you see that 1 plus h, that's where the x must have been. That is where, because what do? You do f of 1 plus h, you plug a 1 plus h in to the function. So that's what they did. They had plugged a 1 plus h into the function. This must have been the function. And the a value was
1.
this number right here, 1. So this must have been finding f prime of 1. So you were supposed to, now let me do this in red, you were supposed to put this red piece, not the limit, but just the red piece into your calculator. So Rachel, if you would do that for me. She's going to put this red piece into her calculator, except now those of you who are gone Friday, if you didn't get a chance to see the video, there's going to be one problem with putting that red thing into your calculator. What is it? The h. The h, right? You can't use h when you put that into your graph screen. You can't put h. You got to put an x, right? So instead of h, we got to put an x. So instead of as h approaches 0, we have to put, think of it as x approaches 0, right? Because we're going to do a table here. We're going to do a table. Okay, so Rachel's putting that into her calculator, and we're going to do as h approaches 0, not h approaches 1, right? That 1 is different, right? That's where what we're finding is the slope at 1. But the limit problem is as h approaches 0. Okay? So she's about to do that, or is doing it, or has done it. Okay? So she's in there. She put that into her F1. On the graph screen, she's hit Control T for the table to bring up the table. Control T is how we got the table there. And she's brought that up. She went in. Go back to your menu again. Let's do that one more time. She went to Menu, Table. She went to her table settings. She started that at 0 because we're doing x's approaching 0. She put in 0.001, or you can put in another 0 if you want. Hit OK. Okay, and then she arrowed up a little bit. And so I told you you did not have to copy down the table on this worksheet, but arrow up another one. But we want to look at these y values in the table, and sure enough, they're meeting at where? 0.5. We got 0.500, 0.499. Clearly, those cars, if you will, are approaching 0.5. The limit from the left, the limit from the right, as h is approaching 0, we're coming in at 0.5, which of course we just did with algebra a minute ago. We got 1/2 as our answer, so we went 0.5. Okay, and that's what you were doing on the worksheet, just using the table to do the limit, but we just showed how same problem, we could do algebra, we could do a table, right? And then of course if we have graphs for our function, we can do limits with graphs. All right, back back to the worksheet real quick. Thank you, Rachel. So we said that this was also, but here's the thing. There's no algebra I can do to this yet. There's no algebra. I can't distribute a sign. That doesn't work. There's no algebra I can do to this. There's no algebra I can do to that. So the table, the calculator table, is kind of the only way, right? Now, it turns out these are all derivatives, so what we'll do in Chapter 3 is we'll be working on our derivative rules, so we won't have to mess with them, right? We'll be able to find derivatives with a bunch of derivatives. All right, this one was more of the simpler one we did with our factoring. If we FOIL that all out, we get something like that. These are the very first ones we did at the beginning of the year. Beginning of the chapter. We take out an H, right? We got that. The H's cancel. And now we let H go to 0, and you get 4. You get 4. Right? You get 4, which is the same thing you should have got when you did your table on that one as well. But that just a little more practice on the fact. Okay? All right. So, going back to our quiz review, we've been pretty thorough. We've talked about that idea with continuous functions. We talked about differentiable. We spent a lot of time on chart stuff. We've just went through examples of all of these different things here. Really, I mean, the part I skipped is I didn't try to plug in a 0 or whatever into any of those limits we were doing, but we would have gotten 0 over 0 on all those. So we've got that scenario. We've done some of our shortcut with our power rule. You know, we did the graph thing. I'm trying to think what else I had down here as something to maybe do. A chart thing with graph. Aaron asked about with the big F, capital F. Let's do something with that here in a second. And then, of course, the long way of doing it. Now, let's make a comment about that before we go to this last thing here. So if I ask you for f of x, let me just get you started on one. So let's say I did something like this and said find f prime of 1 by the definition, right? Let's go back to the very beginning of chapter 2, right? Go back to the very beginning because I said you're going to have to do this at least once, right? Now we just got done doing numbers 5 on the worksheet, right? Think about what we just did on number 5, right? That algebra we did. That's really what it looks like. Now, the difference is the limit was already set up for you there. So the other thing we should practice real quick is, how do I set that up? Okay, well, what is the definition? It's f of x plus h minus f of x all over h, right? That's the definition of the derivative. So that means we want to do f of
3x.
Well, wait a minute. F of 1 plus h minus f of 1 all over h, and I forgot my limit out front. Okay? So what's f of 1 plus h?
3.
Sub that in for the x, right? So it'd be 3, 1 plus h squared, plus 2, 1 plus h. So that'd be the f of 1 plus h part. Minus 3 plus 2 is 5 all over h. And that's a limit as h approaches 0. And we'll stop right there and you can finish that. But now all that'll be left is the FOIL, distribute, simplify the top. Hopefully something nice will happen. 5s will drop out. You'll be able to take out an h. You'll be able to cancel an h. You'll be able to plug a 0 in for h, right? Everything from here on out would be just like what we just got done doing when we did number 5 on the worksheet, right? So now we know, of course, already. So in blue, we'll just top secret, pretend we can't see it. We know the derivative of f is actually what? Because we've learned our shortcut now, right? So we know the derivative is 6x plus 2. So f prime of 1 we know is 8, right? We know that f prime of 1 on this problem is going to be 8, right? So hopefully when we work that out, that's what we come up with, right? So that's our shortcut. But if it says do it by the definition, right, this is what we do. All right, so last thing I wanted to look at is, if you turn in your books to page 120, this is on section 2.4. This is more chart stuff, and Aaron had asked about it. We had introduced the idea of big F, right? Big F, we called that the antiderivative of F, which just means in our chain of derivatives, right? F, F prime, F double prime, da da da. It would be the one above F. So going down, you're just doing the derivative. So the derivative of big F would be the same as little f, and so forth and so on. That's all it is. This is numbers 13 through 18 on page 120. Okay, so I think, yeah. And those were not ones we did. We had done the other section over there, 3 through 12, which was essentially the same kind of thing. So I wanted to talk about this. So it says that big F, now let's think about this now, because this was a key part of last quiz. It says big F is the antiderivative of the function little f, right? So they're just saying what we already have said. Big F has a root at x equals 8.8. So if I go over here to 8.8, that's like right here. So what graph is this that I'm looking at? From those directions, we've got to make sure we understand what graph we're looking at. Isn't this big F? Now on 3 through 12, I think it was different than that. It said big F is the antiderivative of the function little f shown below. Right? So there, that graph was little f. This graph is big F. So it's very important in reading the directions we understand what graph we're looking at. Okay? All right. So then it asks you all these questions. So it tells you about where it crosses and what those numbers are. Where is little f positive? Well, so we're thinking of the chart. Little f is positive when big F is. So when is this graph increasing? From there. And they tell us in the directions, where is that? It tells us where the stationary points are. So this would be 3.2. This one is 6. What? God, that's awful. So they're saying this is the max. Okay, yeah, whatever. They said the max is right there at 6. And 13.3, which is right here. Yeah. So our answer would be from 3.2 to 6, and from 13.3 to 15, right? Okay, number 14. How many roots does little f have? So when is little f 0? Which are those 3 points right there. Little f would have roots, meaning little f would be 0 at those stationary points, okay? Right now, let's skip that for right now. Little f of 10, so little f of 10 would be, wouldn't it be this slope right here? So we would do a rise over run kind of thing. So it looks to me like I go over 1 and down about 1, looks like, pretty close. Maybe not quite 1, -1, -0.8, something like that. Okay, where is little f increasing? Little f is increasing when big F is concave up, right? All this is stuff from the chart, right? So this kind of thing I might ask you about an antiderivative, but not that rule thing we were talking about, going backwards with the power rule. Don't worry about that, okay? So this is all just, so where is it concave up? Well, it's concave up looks like from 0 to, did it tell us where this inflection point is? 4.5. So this is at about 4.5. So concave up from 0 to 4.5, and 10.5 is this inflection point, concave up from 10.5 to 15. Okay? But again, those are just things, if we know this order right here for our chart, right, that would just carry right over to over here. So I know that I could have this row be big F, this row would be big F prime, but that's the same as little f. And this row would be little f prime, which is the same as big F prime. As long as you know that relationship, then your chart, all your chart stuff is there. So that would be the only thing I would even mess with if it came to anti-derivatives. Okay, that's it. So you guys that were gone, you've seen it all. I mean, that's pretty much. If you can do any and all those things that we have done there, that is what we have done over the last number of days. Now, if to study for this thing, let me give you a few problems. Now, these problems have, as I went through them, I looked at the back of the chapter and looked for some in the review kind of sections. They don't have a very good set of problems there. I mean, they're really good problems. They really make you think about some different things, but I don't want to add more to your plate. So to be honest, I wouldn't put a big priority in working these. If you feel pretty comfortable with all the different things we've done in our homework over time, then I would say you could do these a little bit. This is starting on page 150, I believe. This is more, there are some power rule problems in here, you know, where you bring the power down in front. There's some kind of wild ones with radicals and fractions and stuff. You have to do a little of that, but not very much. So 3, 4, 5, 8, 11, 13. People are often wanting some new problems to look at, so I went ahead and found these, but
22 or 23?
That's a 23. Okay, so I found some, but that is certainly not a complete picture of things. You're better off looking at all the things we talked about, the review that we went through there, the notes we took, practicing like on the worksheet, the old algebra ones, your techniques on the algebra, because there isn't any of that in here. Okay, so this is a few things that you should probably be able to do, but some of them are worded a little differently than we did. So if you have a pretty good comfort level with stuff, this would be good to look at. But otherwise, going back over the old homework and the things we've talked about today is where you want to be. Okay?
I would have done this, but you didn't say.
Okay, Jordan's already told me he's going to be gone tomorrow, so if you have any other issues about the quiz or whatever, please see me.
Yes, I'll be gone tomorrow.
Okay.
And then do you want to look at the homework?
Yeah, let's see. I looked at the homework on Thursday. I don't think I did on Friday. So Thursday, so that'd be 2.3. Okay.
And then the worksheet.
Yes.
It's full on the quiz. If we do anything with like intervals and it has a closed graph, do you want us just to go to the edge? Or can
Yeah, like that, where it's got the box. Just go to the edge. Okay. Gotcha. Good. And you're gonna be gone. And you're gonna be gone. And then, okay. So then we got to think about when. Are you gonna be gone like later in the week too? Jordan's gonna be gone.
I am. I won't.
Are you guys
I'm
at the
gonna
same
be
place?
gone Thursday and Friday. No, he's going to Allstate. I'm going with college.
But you're gonna be gone tomorrow, Thursday, and Friday, which is the same days you're gonna be. Tomorrow, Thursday, and Friday.
And next Tuesday. We're just like awesome, aren't we? Go school in November.
Thursday, Friday for you too.
No, I'll be here
You'll be
Thursday.
here.
We'll be gone Thursday, Friday.
Allstate people are gone Thursday and Friday.
Oh, okay.
And Aaron and Jordan and Katie and Megan Faulkner.
I'll be on.
I might. I'm gonna.